any other edition, it's practically about the same information, but when we have assignment or exercise, you should use the 4th edition, okay? Because they are not the same questions, so that you'll not be answering a different question, all right? Okay, so this week we'll be dealing with motion in 1 dimension. Motion in 1 dimension, all right? And I just love the intro in this, the chapter 2 beginning. It says something about the us and the human. I know some of us who must have known this, but some of us will be seeing it for the first time, that it's actually possible for humans to outrun animals, okay? But that only happens at a certain distance. And this is interesting because it is actually the understanding of motion in 1 dimension that brought about this finding, all right? So I just put a link there just to explain, but it's not really so important to us, but something just fun, okay? So begin first by describing what motion is, and we have done that in chapter 1. We established that we describe motion in terms of position, acceleration, and velocity, all right? We use these 3 terms to describe motion. But the major block of our discourse on this topic will be the uniform motion, the acceleration, and the free fall. So we'll be taking it, the first contact, we'll be discussing the uniform motion, and as it relates to uniform motion, interpretation of graphs, understanding the description using position, velocity, and then by second contact, we move to the details of acceleration, and then third contact, we just talk on free fall, practice questions, and we'll be done for the week, okay? So these 3 blocks we just talked about are represented here. When we talk about uniform motion, we're talking about motion with steady velocity. We're talking about motion with constant velocity. And then we'll have the acceleration, that is motion with, from the definition of acceleration, the change in velocity, but steady change in velocity as well. That is talking about constant acceleration. And the free fall motion. Simply put, motion of object in air, okay? So continuing our description of motion before we talk about the uniform motion, we see that when we want to describe position, we actually make use of coordinate systems, okay? At this level, we just limit ourselves to 1 dimension. We'll advance by next week to 2 dimensions. So when we talk about 1 dimension, we're talking about motion in just 1 coordinates line, like the x-axis or just the y-axis, okay? So we have that in describing the direction of motion in respect to position, we have the motion moving or object moving to the right. We just pick the 0 point as the point of origin. It's not always starting from 0. Motion don't always start from 0, but the point of origin helps us describe the direction of that motion, okay? So to the right side, x is greater than 0, and to the left, s is less than 0. And same applies to the y-axis. When it's going up, that is to the right, y is greater than 0, and down, direction is y is less than 0, okay? So we'll use both the s and y axis to describe the exact position of any motion. We saw this in the description of chapter 1 when we described the pictorial representation, and we move on to describing the vector, velocity vector representation of motion. The only new thing here is just the acceleration, which we'll talk about in details by second contact. So we'll have that we can actually put these two description of motion into graphical representation when the emphasis is on describing its position, okay? So we understand that better using the graph system. This is just an example of the motion of the car here, represented in the vector diagram and in its graphical form. Okay, now the representation of this motion, like we saw in the previous slide, having represented the motion in the graphical or vector diagram representation, we can actually extract this into a table and further describe it using a graph. Okay, so let's take this example of the student walking to school. Looking at the vector diagram or the velocity diagram, the velocity vector representation of this motion, we can see that this arrow, the second and the third, they are of the same length, right? And that tells us what? We can just drop that in the chat. When we have equal steady distance, that is arrow of the same length, what does it mean? Exactly. Good. So the student is actually working at a constant velocity. Now the student velocity decreased, but it also maintained a constant because these, they are the same size as well. Then the student also increased speed and then had the same length of arrow to tell us also that it maintained a steady speed. How do we represent it graphically? First, we extracted the table to get the figure, to get the plot for the graph, okay? So from the values here, we can see the steady increase, constant interval, same spacing in between the two, is covering the distance. Then we have constant, and then we have the same thing too, then 100, 100, 100 as the spacing here. So in describing this, because this is actually the emphasis, we already know this. Our emphasis in this class is how to use the graph to understand the motion and also use it to describe position and describe the motion of any moving object. Now, if you send me a chat and it's very important that you have to interrupt the class, just come on the mic, pause, okay? Because sometimes I might not be reading the chat, okay? Can you hear me?
Yes.
And can you see my screen?
Yes.
Okay, good, thank you. All right, so now we notice that the first steady movement, we see the steep of this line decreased, but it's also advancing in the positive direction. Remember the position signs that we just saw? When it's on from 0 to the right, it's positive, okay? When it's going this way, it's negative. Or when it's going to negative, the motion direction is actually going to the left, okay? Or down. When it's down, it's going to the left. Up, going to the right. Same also for the x-axis. So with this understanding here, let's take one example. Okay, I want to mention that this is actually the x here is not the axis like x-axis in coordinate system. It simply means the position or displacement axis, all right? And this is the time. Okay, so we'll have the position versus time graph. We'll have the position and the time. So how do we describe motion or interpret motion of a moving object using the position time graph? That is what we want to see next, okay? So let's take one example. Our first example here says, the graph represents the motion of the car along the straight road. And the question is, describe the motion from this graph. So we want to put this graph in words, all right? So first we take a critical look at the calibration or the reading for the graph. We have this y-axis to be the displacement in kilometers and the time t in minutes. So it means when you want to describe in words, you'll be using minutes and kilometer, not seconds, like you know it's the unit of time, okay? All right, so we see that the car traveled to the left. And how did we get this information? It moved down, okay? Remember we said when we have a down movement or to the negative S direction, it is actually a left movement. So the car moved to the left for 30 minutes. So this time spacing here is 10, 10, 10. So we have movements for 10, 20, 30. Okay, 10, 20, 30. Move the distance of 30, 30, right? And then had a pause for 10 minutes. From here to this place is 10. Then proceeded to the right, which is the upward direction, for 40 minutes, which is 10, 20, 30, 40. Now we're able to conclude that it ended up where it started because it ended up at the 0 position, okay, 0 point. So this is just the description of this graph. Let's see how we analyze the graph, okay? So at the start point, time 0, the car, yeah, was at 10 kilometers. That is its origin. Then it moved by decreasing its speed for 30 minutes. Then it waited for 10 minutes. It was steady, didn't change, or we'll just say the car stopped for 10 minutes, then increased speed for 40 minutes. Okay, indicating that it moved to the right because it went upward. Left, wait, upward. Okay, so when you're asked any question like this, there are things we look out for when marking the question or marking your description provided. We want to see if you emphasized the position, the time, okay, and the direction. Right, we'll see that later in the test. So just like we had the conventional sign for the position, we also have for velocity, okay? So this velocity vector representation, when it's moving to the right, V is greater than 0. To the left, just like the position, less than 0. Same for upward and downward direction as seen earlier, okay? So what are we trying to emphasize in this by this? We want to emphasize that the speed is actually the magnitude of the velocity vector, and it's always positive. So when you see a negative value, we are just not talking about the magnitude, but the velocity. Okay, so we can have positive, negative velocity, but not the magnitude or the speed. Okay, so we also want to establish that the position versus time graph, the slope of that is actually the object's velocity, and that is represented with this. So just a slope of the graph can replace this with a V is equal to changing X over changing T. Okay. So, and the principle holds that the negative slope corresponds to a negative velocity. All right. So whenever we have a negative slope, it's a negative velocity, but we're not saying the speed is negative. Okay. Because speed is actually the magnitude of the velocity vector. And magnitude, like we know earlier, is always positive. Okay. So I mentioned something earlier that when you're asked a question, especially when you're asked to describe the motion of an object from a graph, you should be able to tell us the object's position at that time. That is, looking at the graph, mention its position or direction at the specific time interval. Also mention the object velocity at that time. Then note that the steeper the slope, it corresponds to the faster speed, like we saw in the very first diagram. Okay, the graph representation of that car or student walking to school. We saw the first tip was higher than that of the middle, and then the last one was the steepest. Okay, so we also know that the direction is important to mention the direction if it's going to the left or to the right, or because that will tell us if we have the negative velocity or positive. All right, you can practice this in when I say exercise 3-4, I'm actually referring to the problem section of the text. Okay. I keep using exercise, don't mind me. Okay, so I haven't known that we can actually say a lot from the position time graph. And we have established also that the position time graph can actually tell us the velocity of the moving object. How then do we describe or deduce the velocity time graph from the position time graph? How do we do this? Okay, so this is the example of the position time graph we saw earlier. We want to deduce from this graph the velocity time graph. Okay, so to do this, we have said we established that the slope is actually the velocity. Okay, so what we do is from this graph, we notice that this graph is separated into 3 segments: this to this section to this, and this to this. That means we have to represent these 3 segments in the velocity time graph. And how did we do this? By taking the slope of each segment. So we took the slope here, which is change in S. We can see that the change in S, 180. Then here is 3. So we have 180 over 3 to give us, then in minutes, we convert from minutes to seconds to give us this, okay, 1. So we came to the velocity time graph. We came to the position 1 on the velocity axis. We drew a line and stretched to cover the time. Remember the definition for velocity? Displacement, change in displacement at a time interval or over change in time, okay? So for 3 minutes, so we stretch this line to the 3 minutes, okay? So we came to this section again, took the slope, got our value, took note of the time stretch, came to the position of the value of the slope, which is 0.33, drew a line, stretching it along to the time required. We did the same for this. You notice that this place is steeper, so this one is less steeper. Then this one is the highest, so we can see the different steps in the velocity time graph. So we have something like this. This and this, we just use a dotted line to join them. So this representation is actually the velocity time graph version of this position time graph, okay? So let's just take one example on that. So this is a position time graph of a car. And the question says, draw a car's velocity versus time graph and describe the motion from the velocity time graph, not from this one, okay? So let's quickly look at that. What we'll do is, before we go to the solution, we'll take the slope. This is a negative slope, so we already know where the line will be on our velocity time graph is going to be on the negative side. Then we'll have the horizontal, the slope on the horizontal is always 0 and the slope on the vertical is undefined. All right. So this, we already know this is a 0 position, and then this is the upward, which is the positive direction. So we'll have taking the slope on this side, the slope gave us -2. We came to -2 position, stretch. This ended at 2 seconds. So stretch this to 2 seconds. Also, the slope here is 0, and this is a 0 position for 2 seconds. That is this to this. We stretch that, and then we came to this. We took the slope of this, and it gave us 5. We came to the position 5, drew a line for the number of for the length of time as well, which is 4 to 6. 4 started at 4 and ended at 6. Okay, so this is the velocity versus time graph for the car, which is the object in motion. So we'll describe this looking at this diagram now. The velocity time graph shows us the motion of the car. From the diagram or the graph, we can see that the car moved back, that is, it went down or to the left direction for 2 seconds, waited for 2 seconds, then began the motion again, accelerating or increasing speed for 2 seconds as well. Okay, so we see this, the wait time and the acceleration. All right, so if we could do the deduction of velocity time graph from as a position time graph, we should also go in the reverse way. We are able to also deduce the position time graph from the velocity time graph. And how do we do that? Just go in the reverse way, like I said. It means from your equation Vs equal to change in S over change in T, you know the time and you have the slope, and you're looking for the X, which is changing the X, okay? So if you make that the subject of formula, you have that if your slope is 1, do the reverse in the equation, and then the time is stated 15. So when you do that, that means you have V is 1 over X equal to X over 15. If you cross multiply this to get the value of S, you have 15. That means starting from the origin, because we see that when we have the velocity time graph value, it means there's a steep line on the position time graph. So we took the steep line straight from the origin to the position 15. That is this line here. Then we'll have this in the negative y-axis and positive x-axis. This tells us a negative or left direction. So we do the same, put in -3 equal to x over this place to this place is 5 over 5. And we got 15. So we went from that 15. We moved 15 distance, 15 meters down. So we ended at the origin. If we are to describe this in words, we'll be able to say that there's a forward motion for 15 meters in 15 seconds, and then this for 5 seconds. So when it was going down, it moved faster than when it was going up. All right. So we're having some practice question on this. So now with that description, we'll also be able to describe perfectly what a uniform motion will look like in terms of the velocity time graph and position time graph. So when we talk about uniform motion, we're actually talking about motion with constant velocity, motion with steady unchanging velocity. All right. We also have constant acceleration, but that is different from the constant velocity term in terms of uniform velocity. And we'll be looking at this in our second contact. We'll be also emphasizing that acceleration is not only talking about the forward motion, but also it can be in the reverse motion, all right? So from this, we saw in chapter 1, the even spacing representing a steady change or a constant velocity, all right? Also in a vector, a velocity vector representation, the arrows will always be of the same length, okay? And that is what we see here. This is a uniform motion. We see the displacement having equal spacing, which is represented with equal arrow size. All right. And this points us to the direction of the motion. Okay. So if you have a situation where you're moving, we use the word perfectly steady because sometimes it's not easy to attain the perfectly steady state, especially when you're driving. Although it is actually the concept of uniform motion, motion knowledge that helps in the technology of the cruise system in cars today. But even when you engage your cruise system and it's moving at a steady speed, sometimes the sensors around the car will be able to, okay, bring the car to a stop, and then you don't have a perfect steady state. But let's assume that we'll have such perfect steady motion and we are moving 60 miles per hour. If that is maintained, you'll be able to tell that in the next 60 miles, in the next 1 hour, I'm going to cover 60 miles. And in the next, I'm going to cover 60 miles. So if you're able to say, if you're able to establish that nothing will change in the motion, you'll be able to tell exactly where you will be in 3 or 2 hours time, or even in 5 minutes time. Okay, so such a system of motion is what we call the uniform motion. And how this is represented in a graphical form, we see the same way like it is here in the arrow, the dot spacing or in the plot of values you get, we have the same value. As S is changing, Y is changing also in a constant, steady manner. All right. So we have equation to describe this. And the equation to describe this also stemmed from the velocity equation, where we have the V equals to change in S over change in T. All right. So we emphasize the change in S to be the rise and then the run, which is the time you covered. This is just the same, this is simple, the way we attain the slope. To use the S final to talk about the displacement at the final position at the start, and the same thing, the initial time to TF standing for the final time, okay? So from this relationship, Vs is equal to XF minus SI, TF minus TI. We're able to derive this equation, and this is what we now call the position equation for a uniform motion, okay? This equation here can also be written in this form, because when you move this to this side, it becomes changing X, and you have this on this side, you have the velocity, which is changing X, or your displacement is actually the product of your velocity with time. All right. So what we should note when talking about uniform motion, we should note these 3 things. If we forget any other thing, don't forget these 3 things, okay? that in uniform motion, acceleration is 0. Acceleration is 0, but the velocity is what? Constant. And the position is changing in a steady manner. Okay, so these 3 points is just what defines everything about uniform motion. So if you have a motion with a change in acceleration, that automatically tells you it's not a uniform motion. Okay. This concept is different from the concept of constant acceleration, which also means a steady change in acceleration. Okay. So what other way can we actually find, apart from what we've seen now from the graph, can we actually use other method to find the position from a velocity time graph or velocity from a position time graph? Yes, that is the answer. And how do we do that? By taking the area under the graph. Okay, so we have an example before us. This is a displacement velocity time graph, and we want to obtain the displacement from this. And because we have just 1 point, how do we do that? We can do that by taking the area under the graph. Okay, if we have the selected portion or area under the graph as defined by time, we'll be able to take the get the displacement. The area of a rectangle is length times breadth, right? So we'll have the length with 12 times the breadth to be 2 seconds, 1, 2. So we have 12 times 2 to give us 24. So we'll have the displacement by taking the area under the graph to be 24. Okay, we can also do the reverse to get the velocity time graph by taking area under the graph. Okay, so that brings us to an interesting term that we'll call instantaneous velocity. Remember that when we're talking about the steady change in the motion of an object, we use the word perfectly steady. That means that we'll also have cases or scenarios where there will be a steady change, but the changes are not perfectly uniform. Okay, like we saw in the example of the student walking to school. We had a time it was steady, it changed and became steady again, but it's not a perfect continuous steady state. Okay, so we have a good example of that in the motion of a car that is trying to join the express from a ramp, or on a straight road trying to merge with the lane. We notice that the car can be maintaining a steady state, a steady motion, but it's changing. And then when we take a plot of such motion, it gives us a curve. And from the curve, we can also use the principle that we already know about velocity time graph or position time graph, or the definitions we know to do that. That is establishing that the slope of a displacement time graph will always give you the velocity, right? So we'll have the example of such a motion. And in describing the velocity of such a motion, we use the word instantaneous velocity. And what is instantaneous velocity? The object's velocity is speed and direction at the specific instant of time. Okay? At the specific instant of time, we call such a velocity instantaneous velocity. That means it is the velocity of this object at this point. Okay? The velocity at each point. It's the instantaneous velocity. So if we take the velocity at a point, we know how to take the velocity or slope of a curve by drawing a tangent, a line, a tangent on the curve, get our rectangle, and then we'll get the slope. So this is 60, and this is 0. So we'll have 60, and this will give us 4. So we have the velocity at the instant to be 15 meters per second. Okay, so we can just, this link is just to show you the different signs. We have the positive curve, negative curve, how the curve. Just click this or copy this link to check the different curve signs. Okay. Okay, so let us try to practice some things. Do we have any comment? Good, 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 good. Can you all hear me?
Yes. Yes.
Good. Okay, so we have been able to do 3 things in today's class. I've been able to know how to interpret the velocity time graph, the position time graph. We know we have the information about the uniform motion, how to describe or the points or things to emphasize when you are asked to give a description of a motion from a time graph. Okay, note that please, because your score will border around those points. Okay, so let's try to see if we recall everything we have talked about in this last 35 minutes. All right, so this is just a simple reading quiz. The slope at a point on a position time graph of an object tells you what? I like to see the answer in the chat. C. Okay, okay, good, 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 good. Instantaneous velocity, yes, yes. So that's just the last thing we just discussed, that the slope, the emphasis on the word point, okay, gives us the instantaneous velocity. All right. So C is our answer. And what will be the answer for this? The area under the velocity time graph will give us what? D. Yep. D. Interesting. The area under the velocity time graph will give us the displacement of the object. Okay. So how about this? I have just 3 minutes. I'm going to skip this, skip to the description of the graph. Yep. This. Which of these graphs is a description of this motion, this diagram here? Which of this velocity time graph matches this motion? Okay. Remember, it's velocity time graph, not distance time graph. If it was to be distance, displacement time graph, you will notice that this would be a perfect match if this was X, okay? So you have steep to this, then this, but this is not X. So if you want to get the graph for this, you make something like this, then take the slope to give you the answer, okay? So let's see if we have answers. Yeah, C. Yep. The answer is actually C. Okay. The slope, then a steeper slope will give you this. Okay. So we'll have lots of practice question in this under this topic. Okay. So let's check this. I know in the lecture notes we already have the answer, but what you should do is try not to look at the answer first. Just see how the answer came to be that answer, and you discover that no matter the twist the question, you'll be able to get the answer, right? Do we have comment or question on that? Any comments? You're free to tell the class something you read, an information that was useful, it could help another person, not just question. You can comment, you can say, bring in your contribution, okay? I'd like you to come on the mic if you have a question or a comment. Osia, would you like to come to the mic? Are you there?
Pardon me?
Okay. I'm listening to you. You were asking a question. You said since.
Yeah.
Mhm.
Because vectors can't be negative, it would be D unless we're including the negative as an indication of direction. Is that right?
Okay, for this question, right?
That was my question, yeah.
Okay, you said since the vector cannot be negative, it will be D. That is, you're referring to the question on the screen right now, right?
Yep.
Okay, so let's go to that question. So the graph of the position versus time for this is represented this way. And yep. Which of the following velocity time graph gives us blah, blah, blah. So for the position, we established that at 0 or horizontal line for the x direction, the slope is always what? This 0. So we'll have the 0 and the slope here. If you take the slope, you see that the slope cuts across positive direction, and that information Osia just provided helped us. But the final answer of the value we got is stretched at this time. So that is how we got D. But if, Osia, are you still there?
Yep.
So you chose D as your option. Am
Well,
I correct?
we're using a positive negative coordinate system to indicate direction.
Yeah, but with this slope of position time graph, what can you tell us about the direction of
Well, it's
this?
a negative slope. So it would be C in this case. I just wasn't sure.
So if it's a negative slope, that automatically tells you what the velocity will be,
It would be considered
right?
negative velocity. Okay, thank you.
But what we said about velocity is that velocity value can be positive or negative, but the magnitude is never negative, okay? And the magnitude of a velocity is speed, all right?
Thank you.
Okay, so you see how we arrived at our C, negative direction. The slope will give us a negative V, and there's no slope here. All right, do we have another person? Thank you, Sia, for coming to the mic. Yep. Okay. So same apply to this. We're taking from this velocity time graph, we want to bring out the position time graph. How do we do that? Which one is the answer? Don't go to the answer, just try to look at it first from the diagram. D, 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 D. Okay, so if we're choosing D, yes, looks like it, because from here we get a steep. But we already know that the 0 here means the line is straight horizontal. So, okay, so we're able to do the stop and think solution on our test, right? And I noticed also that we have only about 8 persons that have turned in their assignment for the week 1. The assignment for the week 2 will be coming on a Friday. Yeah. But I've put, it's not going to be something too different from the practice exercises after the class or each contact. So if you're actually going to practice those to turn in the assignment or do the solution will not be difficult. All right.
I have a question about the assignment.
Okay.
Can we hand in the assignment as a PDF?
Yes.
Okay, thank you.
You can hand it in whatever form that you think I can read. Okay. What I mean by I can read is what my system can read. Right now, it can read Word, pictures, and PDF. That is JPEG. Okay. Because someone
so-
said. Mhm.
Oh no, you can continue. I'll ask after. Sorry.
Okay. All right. Okay, so we have just 5 minutes left to interact, but you have some personal practice. In our test on page 38, we'll see the mathematical relationship, information, something about ratio and all that. I'd like you to practice that and study the example 2.4 and example 2.5. I have this lecture module in the PDF and PowerPoint form too. So you can solve problems 3, 4, and 11 of chapter 2. Okay. So you have to solve that under the problem section, not the question section. I believe that every one of us have access now to our text. I don't have to copy this out for anyone, right? Okay. Thank you. All right. So at the end of the week, because this is where we'll be starting our next contact, we'll be talking about acceleration, constant acceleration. We'll solve some examples. We'll note the signs. So I expect that you would have gone through this, compare the slide section to what you have in your textbook. Then when we are discussing in class, so it can be just a free flow. We'll be on the same page all through. Okay. All right. I will encourage us not to keep this till when it's towards exam, because it will be too much for us to read. We have chapter 1 to 13 to cover, and we're covering each chapter in 1 week. Okay, so we're covering chapter 2, and we hope that at the end of the week, by Friday, we are done with chapter 2, dusted, ready for tests, exams, or whatever from chapter 1 or 2, right? Great. Okay, so you practice this because I'll be pulling out the working examples or assignment for the week from something similar to these practices, all right? Okay, do we have any other questions?
Yes, are you posting these slides on Moodle?
Yes, they are already on Moodle. The PDF and the PowerPoint version, depending on whichever. I noticed that when I downloaded the PDF on a different laptop, the arrangement scattered. So that was what informed my converting the PowerPoint. Oh, no, sorry, I missed the word. When I downloaded the PowerPoint on different laptops, on a different laptop, the arrangement was scattered. So I had to be converting everything to PDF and also putting it in PowerPoint in case you need to extract some portion of the class to print as a tip to put on your wall or something. Okay, so you have the PDF and the PowerPoint version, then the link. So the link for the classes, I usually put the C1 to save contact 1, contact 2, contact 3, because we have 3 contacts in a week for the online lecture and 1 contact for the lab classes. Okay, did that answer the question?
Yes, thank you.
I have a
welcome.
question just regarding the tests. Like,
Okay.
how are we going to be doing those? Like, I know it like is online somehow, but like just like yeah.
Okay, so just to have an idea about the test, I put up something I put on the module called lab quiz. You can try it before the lab and also try it after the lab. Will have about 8 attempts. So that will give you an idea of what the test will look like. And there will be some sections where you'll be required to show your working. I'd like to see, and if it will mean you uploading just the same way you turn in assignments, or yeah, the same way you turn an assignment, or if we have alternative way or information to see you work it while we view, we will tell you too. But I know that the test will be online, but the exam is going to be in person.
Okay.
Okay. All right.
I have a
Okay.
question.
I'm listening to you.
The lectures, you're
Mhm.
recording it. I'm just wondering if we'd be able to gain access to it. Are you going to post it on Moodle so that we can go back to it whenever needed?
Okay. Yeah, I'm at liberty to post or not to post. But okay, if you request for it, I'll do that. It will be available.
Yes, please. I would greatly appreciate that.
Okay. All right,
you.
I'll do that. You're welcome. Okay, do we have another question?
I have a question about the midterms scheduling.
The midterm. Mhm.
On the syllabus, it says that our first midterm is October 17th and the second one is November 7th, but those are Sundays.
Yeah, I said it at the beginning of the class that I'm going to correct the time for the lab and the midterm because they are wrong on the syllabus. All right. Once I post the corrected one, I'll send a mail to everyone. Okay. So that is not the right time. All right. It will be
Yep.
corrected. Okay. And I also said I'll send information about the lab, and I'd like you to go to the lab section on Moodle, get all the materials there because some of which are samples or templates of how you're reporting your lab, then the introduction, and then 2 practicals or lab experiment that will be performing on Wednesday, the error measurement and brass cylinder. Okay. So I believe we all have access to the lab materials now for the Wednesday lab. It's on Moodle.
On Wednesday?
Yep. I said I'll send the time and venue because what I have on the syllabus is not the right time and venue. Okay. Okay, someone is asking, can you come on the mic? I'd like to hear your voice. Damola, are you there?
Yeah, I was just asking if we are printing off anything for the lab section.
Okay, yeah, I'll encourage you to print out you see the where you have lab. Let me go to the module and be sure I'm quoting the right document. You're expected to come with a printout of the lab instruction document, which okay, what I'll do is I'll specify and send it as news to us, the particular document to come with, okay?
Thank you.
You're welcome. Do we have any other question? Okay, if no other question, all right, we'll be calling today. See you on Wednesday morning before the lab, and see you live Wednesday afternoon in my lab class. All right.
All right, thank you.
Thank you so much. To have a
Thank
wonderful
you.
day.
Bye.
Bye bye.
Thank you.
I have a question.
Okay.
So you keep saying that the lab is on Wednesday, but mine was scheduled for Friday. So do we all have different dates?
Yeah, we have limited numbers of persons to be in the lab at a time. So
Yeah.
for those that were able to pick the Wednesday, we'll be having a Wednesday, and for those of you scheduled for Friday, we also have on Friday. Okay.
Oh, okay, sounds good. Thank you.
Thank you. All right. Bye bye. Have a nice day.